If you could only afford one treatment process, what would you do? I want you to think about this because there are plenty of places on the planet where you can't do everything that you would like to do. And you have to come up with, okay, what's the next step? So if you lived in the town that had that water source and you had very limited resources and you could only afford to do like the very first step in treating the water, what would you do? That chlorination only works if the water is clear enough that when you look at it, you don't see dirt. So that river is not it. Chlorination won't help you a bit with that river. So, okay, filtration has a very similar problem. It is going to clog so fast that it can't treat water that's this dirty. So this is like the cool insight that is not out there in popular culture. In popular culture, you think that if water is dirty, you should filter it. But what we as engineers know is that if water is dirty, the filter won't work. So if the water is dirty, the only option is flocculation and sedimentation. And then you have the luxury of adding filtration, and then you have the luxury of adding chlorination. But they have to go in that order. And doing it out of order just makes no sense. And wow, the number of people that have that one wrong is really, really, really high. And what's interesting is that has huge implications for development work, like people who are working in around the globe and who are saying, you've got a problem with your water supply, let me fix it for you. So often individuals go to filtration and chlorination when those have no chance at treating the water given how dirty it is. Wow, did I rant and rave on that a little bit? Sorry about that. Pretty intense. I'll try to back off and I'll take my meds so I don't get quite so excited, right? Okay. Wow, the effect of chlorination. So we like chlorination because it kills things. And this table gives you tons of data about how fast chlorine can kill things. And I'd like you to focus on that last column that I've highlighted, CT for PC star. So PC star, oh man, I got to define this. So you know the P function, like pH. You didn't know it was a function. P is a function, it means negative log, okay? Negative log base 10. So the P function is negative log base 10. So PC is the negative log base 10 of some concentration, and the star stands for, I've made this concentration dimensionless by dividing by the initial concentration and dividing the final concentration by the initial concentration. So all of that to say that if you have a PC star of 0, it means that you did nothing, and what's coming out of your system is the same as what went in. A PC star of 1 means that you removed 90% because you're down to 0.1. A PC star of 2 means that you removed 99%. You're down to 0.01. Okay, so you would like a high PC star. That means that you're doing a great job of removing things. So to get a PC star of 1, meaning that we're removing 90% of these pathogens, for the first one, for this Campylobacter, it only takes concentration in milligrams per liter times time in minutes of 0.125 to kill 90% of them. Which means that if you had just this low concentration of 0.125 milligrams per liter for 1 minute, that would kill 90% of that Campylobacter. 0.1 milligrams per liter of chlorine is a very reasonable dose. That means that Campylobacter is easily killed by chlorinating, assuming that you can maintain a chlorine dose there for a minute. And if you look down on this slide, so what you're looking for are which are the bugs that it takes a lot of chlorine, a high CT to get a PC star of 1. And the ones that show up are, there's this Mycobacterium, where it takes 17. So remember that number. And now we're going to go look at what happens if we go to, oh, okay. We'll do this one first. Look at this. There's two cholera organisms. They're related, but they're different. They're a little bit different in how they work. And one of them is super easy to kill, so easy to kill that they didn't even bother giving the number. Okay, they got 100% death rate, and so we weren't able to calculate how much chlorine it actually took to kill a few. And then the other one is super difficult to kill. So the question is, how could that possibly be? How could this one organism be so variable that one bacteria cell is super hard to kill and another one is so hard to kill? And the answer is that the one that's hard to kill, when it hangs out, it forms an aggregate of a whole bunch of bacteria. And guess what happens? The ones on the outside of that aggregate get nailed by the chlorine and they die, but the ones on the inside of that ball are protected. So that's pretty cool, but not in a way if you're trying to keep people safe. So the last conclusions, and then we're gonna jump to the gather town. If you look at viruses, their CT values are even smaller than bacteria. So it's even easier to kill viruses than it is to kill bacteria. If we go to protozoans, here's a number that is scary. Look at that number, 7,200. A huge CT, concentration times time, required to kill Cryptosporidium. Basically, it means that you can't kill Cryptosporidium by chlorinating and have chlorine levels that anybody will be willing to drink. So protozoans are harder to inactivate than bacteria. And then there's, if you look at bad bugs, you'll discover that it only takes one Cryptosporidium to make you sick. And that means that when we're trying to remove particles, we should be thinking about, we're trying to get that last Cryptosporidium out of our water.